We're now prepared to take a look at an example of using variation of parameters to solve a system of differential equations. So this system right here, dx dt is 2x plus 10 and dy dt is 3y plus 12, is considered non-homogeneous because of the plus 10 and the plus 12. It turns out that these are it's a completely decoupled system, so we could solve it using standard method of integrating factors technique on each equation. Neither equation depends on the other dependent variable, but we're just going to demonstrate that this method works. So to construct this solution, we know that for something of the form dy dt equals p of ty plus g of t. So let's go ahead and form that first. I'm going to take a moment just to write out the two equations, and I'm going to allow for the existence of a y term as well. Even if it's missing it, I'll just write 0y and then plus 10. In the second equation, we'll have dy dt equals 0x plus 3y plus 12. And so this is going to convert into the system dy dt equals. Now my P of t matrix, in this case, it's the coefficients of x and y, and these are nice, neat constants, so this works out nicely. And then we'll have this the y vector, which just contains our two variables x and y, and then plus our g of t. Well, in this case, g1 is 10 and g2 is 12. So we already know that we can solve this homogeneous system. To find y sub h, we need to solve dy dt equals 2003 times y. Now you can find the eigenvalues and eigenvectors of this matrix, but it's going to turn out to be the case that we will get y1, if you want to call it that. It doesn't matter which order we call them in, but y1 would be e to the 2t 0, and y2 would be 0 and e to the 3t. All right, and this by composition would give us the solution y sub h is k1 times this vector e to the 2t0 plus k2 0 e to the 3t. And you can just see that really it's stating that x is k1 e to the 2t. In other words, the only function x whose derivative is 2 times the function is the function e to the any multiple of e to the 2t, and the function that has a derivative that is 3 times itself would be, well, the derivative of e to the 3t is 3e to the 3t, and so that's why that piece works out. Now to construct x, the x matrix which we're going to need, it's going to consist of our two solutions, y1 and y2 as the columns. So we'll have e to the 2t 0 and 0 e to the 3t. Perfect. So we have the x matrix constructed. To find this particular solution, which is what we're after now, y sub p is going to be the x matrix, which is e to the 2t 0, 0, e to the 3t times the integral of x inverse, where x inverse is 1 over the Wronskian. Okay, 1 over the Wronskian, that's the product of these two diagonals right here, which will be e to the 2t times e to the 3t, minus the product of these diagonals, which is just minus 0, times the x matrix with, remember, these two diagonal components are switched, so e to the 3t, e to the 2t, and then these components just get negated, the original components. Well, they're both zeros, So I'm not going to write negative 0, I'll just put zeros there. And then times g of t. Okay, so g of t is our constant vector consisting of the components 10 and 12. And this gets integrated with respect to t. All right, so now we have e to the 2t 0, 0, e to the 3t, times the integral. Now we're not going to evaluate the integral yet, but we'll get 1 over common bases. We add the exponents, that'll give us e to the 5t, and multiplied by, okay, well now we need to do this matrix vector multiplication, so it will be 10 times the first column, e to the 3t 0, plus 12 times the second column, 0, e to the 2t. And we just have to keep on going. It just takes a little while to process this down. But here, we'll just copy that down right there. So write the whole matrix out. We'll have 1 over e to the 5t times, now this vector will be 10 e to the 3t and 0, plus 12 times 0 is still just 10 e to the 3t. 10 times 0 plus 12 e to the 2t is 12 e to the 2t. And we need to integrate those components. The way we're going to integrate it is just integrate each piece of that matrix, that vector. So I'll have times the integral. Now here I'm going to distribute this 1 over e to the 5t. So e to the 3t over e to the 5t, I can actually write as 10 e to the negative 2t. Okay, a division of common bases. We can subtract their powers. 3 minus 5 is negative 2. And here I'll have 12 e to the 2 minus 5, which is negative 3t. And so I just need to integrate those. And then I'll do one more matrix vector multiplication, because I'll have a matrix times this integrated vector. Okay, so this is going to give me, and I can use technology to compute this, but this will be 10 over negative 2, e to the negative 2t. That way, when I multiply it again, when I take its derivative, then I get 10 e to the negative 2t. And here I'll have 12 over negative 3 e to the negative 3t. Now, we don't need arbitrary constants here because we're just looking for one particular solution to this system. So I'm not going to write a plus c on these guys. Not that I couldn't, but I really don't want to. I don't need those extra constants there. Okay, so now we'll go ahead and write this as e to the 2t, 0, 0, e to the 3t. So matrix times this vector, negative 5e to the negative 2t, and here we'll have negative 4e to the negative 3t. So when we multiply those together, we'll have this first component times the first column, so negative 5e to the negative 2t times e to the 2t 0, okay? We'll have plus negative 4e to the negative 3t, the second component times the second column. And we're almost done. So here, when we multiply those, this will actually cancel because e to the negative 2t times e to the 2t is 1. As you add their exponents, you get negative 2t plus 2t is 0, e to the 0 is 1. So we just end up with negative 5 right there. And then this times 0 will be 0. And similarly here we'll have plus 0 in the top. Here those will cancel out again. We'll have negative 4. And so now we have the vector negative 5, negative 4. Okay, so let's backtrack. What did we just accomplish? We just calculated y sub p. Awesome. Well, we know that the solution, the general solution, will be the homogeneous plus the particular. We have the homogeneous. We established that that is going to be k1 e to the 2t 0 plus k2 0 e to the 3t. Okay, that's our homogeneous right there. Okay, that's what we just figured out right there. And then plus our y particular. So what's the y particular? Well, that's this nice, neat constant vector consisting of -5, -4. Okay. Now, these are just the general solutions for x of t and y of t. I'll put the of t notation in there just to indicate these are the solutions. So the solution for x of t, the general solution, will be k1 e to the 2t, that comes from the homogeneous, plus 0, plus -5. And y of t will be k1 times 0 plus k2 e to the 3t plus -4. And there is my general solution. Again, this could be done without using variation of parameters, but the method actually works out really nicely here. In an earlier video we mentioned, there's a couple of problems that might arise. The first problem being, hey, can we always find y sub h? Well, the reason we could do it here is because all of our coefficients of x and y were constants, and we could have done this, found these solutions one of two ways. We could have found the eigenvalues and the eigenvectors and constructed the solution based on what we know there. It just turned out that this was already decoupled, and so I did that without technology, but you could certainly find eigenvalues and eigenvectors and do it that way. And knowing that for a system with constant coefficients, you'll have k1 e to the lambda 1t times v1 plus k2 e to the lambda 2t times v2. That's really what we did here. Lambda 1 was just 2, lambda 2 was 3. So first of all, if we can't get to this point, we can't carry on. So if these were some complicated coefficients consisting of functions of t, in theory we could do it, but it may not be possible to actually formulate y1 and y2. So then once we had it, stacked them nicely in here, it also relied on the existence of this integral here, and also notice that the Wronskian, if it had been 0, then we would not be able to use this technique. It simply would not work. And then the last part was, well, here we had to make sure those functions were integrable, that you could actually produce their integral, because if you can't, then this becomes quite messy. And, maybe you can't actually make it past this part, so you can only write your solution perhaps at this stage, where you just say, well, y sub p is going to be the x matrix times the integral of that vector, which we can't find. Fortunately for us, everything worked out really neatly here because of all the constants that we had, and we ended up with a really convenient y particular.